Okay, so now we start data converters, and I have kept scan version of answer sheet on the Moodle if you want to see for mid-sem exam. Okay, so we will continue with performance specifications of data converters, and of course, one thing I tell you, like really architecture of ADC or DAC is not something that very strange or is very difficult to understand. It's very simple. What makes design of data converters challenging is actually inaccuracies involved in the design of these converters. Suppose if there was no inaccuracy, everything was accurate, actually data converter design would have been quite straightforward. Therefore, architecture is not, of course, architecture is very important. In fact, you try to change architecture or conversion mechanism to get better performance. However, with respect to inaccuracies, what is important is when you want to design or analyze a data converter, look at inaccuracies. It's not just how it works. How it works, even you don't need anybody to teach you how it works, right? You can just take a textbook and read it. You will understand how it will work. Therefore, right from the beginning, I always look at inaccuracies. Okay. So, this is just a brief review of last lecture. So, this is just an ideal characteristic of ADC, and then as we discussed, the first transition point is at the half of, in fact, this is for example for 3 bits, okay, so full scale is here, and then this is for example normalized to full scale magnitude, and then doesn't matter what is your signal can be current, can be voltage, can be anything else, right? So at this moment just doesn't matter what is analog input. What is important is here, for example, the example, as you can see, we have 3 bits, therefore it is example for 3 bits converter, but in general all concepts can be extended to any number of bits. So there was a center point and there are transition points. So we kept this center point for the first transition point. We kept this center point to be at 0 as we discussed last time, and therefore this will be ideal characteristic of a ADC. So input is analog, output is a digital code. So therefore you can plot these transfer characteristics, and center point of each segment is shown here, and each segment in this transfer characteristics is having width of 1 LSB. Okay. So and therefore you will have noise margin of plus minus half LSB around center point of each segment. Okay. So this was the review of the last lecture. Now we started looking at the quantization error, and again for the same 3-bit ADC. So quantization error essentially tells you, see, everything is ideal here. There is nothing non-ideal. So therefore, even in a perfectly ideal ADC, you will see quantization. And the reason for quantization is because you are assigning one single code to a range of input voltages, and that makes it to have some sort of quantization that we discussed. So now this is quantization noise or quantization error as a function of input values, and the magnitude or peak-to-peak value of this quantization noise, of course, is full scale upon 2 to the power n, which is LSB size. Okay. So then now, from this, now the first specification of an ADC will be what will be the maximum SNR one can achieve with this ADC. Therefore, it is clear, obvious that now you are applying this even ideal conversion, therefore you get this quantization error. Therefore, if you look at it as some sort of noise, therefore there will be some kind of signal to noise ratio specification which will specify, okay, what is the best we can achieve in this ADC. So everything is ideal. Now suppose we have a sine wave, your signal can be anything, And always I call it signal because we don't mind whether it is voltage or current or it is even anything else which can be after all done in the form of a data converter, because who knows, we can have mechanical systems who will do data conversion. So now considering that signal is a sine wave is not perfectly active signal, its slope is not everywhere same, but we assume that okay, it is almost a perfectly active signal, therefore quantization noise or quantization error will have a uniform distribution. This also we showed last time. Then finally the average value of quantization error power happen to be this. So a full scale upon 2 to the power n, which is LSB size. However, this is already, this should be divided by, okay, so you just correct it in your notes. So delta V is the LSB size, full scale divided by 2 to the power n upon square root 12. So then RMS value will be square root of okay, yeah. So now suppose if I have a sine wave, therefore, and is sine wave, this sine wave actually can have any value, right? Can have any amplitude until the peak-to-peak value of sine wave doesn't cross full scale. Therefore, the maximum peak-to-peak can be full scale, it can be below that as well. Now, suppose if you are below full scale, therefore, you will have less signal power. Therefore, to see what is the maximum achievable SNR, it's better to see what is the maximum level of input signal. Therefore, that's why we assume peak-to-peak to be full scale for the sine wave. Therefore, RMS value of sine wave will be this. Actually, this average also is not required. RMS value of input signal will be full scale divided by 2 square root 2. Therefore, ideal SNR, and in fact, maximum ideal SNR that one can achieve with a perfectly ideal ADC having n number of bits resolution will be this ratio of these two power values. So therefore, average value of x square divided by average value of quantization error square. And this, if you just calculate, it is very easy because everything is just a function of n. There is nothing else here, and full scale will get cancelled. Therefore, it is independent of full scale. So, maximum SNR will be 6.02 n. 6 is actually 20 log 3. That is the reason it appears as 6 plus 1.76 dB. So, what does it mean? Means that as you increase number of bits, for every one increase in the number of bits, you will get 6 dB improvement in SNR. Oh, this is just an idea how it will improve. And then 6 dB increase means will be almost twice, will be almost, 1.7 square root of 2. 20 log 3 will be 3, 10 log square root 2, 10 log 2. No, it will be twice. Okay. So just to give an idea of how much will be like corresponding SNR, suppose if you have 6-bit resolution, corresponding SNR will be around 38 dB. If you have 10 bits resolution, corresponding SNR will be 62 dB. So therefore, this means that if really, going from 10 to 2 bits, 12 bits for example is not very easy always. But that means that if you increase number of bits by 2, therefore like instead of n, you will get n plus 2, therefore you will get 12 dB improvement in SNR. These values of SNR are not very high if you look at like linearities, but anyway this is what happens. Means that if you have an analog system, in a fully analog system, achieving a linearity or THT values above 70 dB is not very difficult. But here, even if ADC is very ideal, here just this is the best performance which can be achieved is this, say for example, for 10 bits 62 dB. But you can design an audio amplifier in analog mode which will give you above 70 dB linearity. Okay, so but there are other ways also. For example, you may not have uniform sampling, you may not have even non-uniform LSB. So, but as I said before also, we don't enter into that in this course. So now, till now, okay, we are looking at the ideal characteristic of an ADC, and that was SNR. So we started with SNR. At least now you know that, okay, this is one of the main characteristics, which is SNR. Now we will continue. What else? So finally, if you have an ADC, that ADC is not an ideal ADC. Therefore, it will create a lot of non-idealities in the signal as it converts signal from analog to digital. So what are these sort of non-linearities, non-idealities? Here, first we start with non-linearities. Okay, there are different kinds of non-idealities. Here we look at non-linearities. Okay, so the first criteria, for example, for non-linearity is very famous. All of you are familiar with it. That is total harmonic distortion. Means that if you have a system and then you apply a single frequency to that system, because that system is not linear, therefore it will create harmonics of that frequency. If you apply two frequencies to that system, again, because it's not linear, it not only creates harmonics of those frequencies, but also it creates intermodulation. Non-linearity means that you will get different kinds of mixing of these two signals. So these are well-known characteristics of a nonlinear system. Now look at ADC as a nonlinear system. Definitely it's not perfectly linear. So therefore it will create distortion. Therefore when we talk about signal to noise ratio, if we remove distortion, so we have unnecessarily removed one part of the specifications, which is very important. Because after all, if you apply a signal, you don't want to get a distorted signal at the output of DSP. You would like to take your original signal with some desired processing on the signal, which can include filtering, therefore. However, you don't want in the band to observe any distortion. So therefore, instead of SNR, we define more specific SNR, which is called SNDR or SNAD, signal to noise and distortion ratio. Therefore, considering nonlinearity, we want to look at noise as well as distortion. So this noise, of course, till now is only quantization noise, but of course, when we go with sample and hold at the big input of any or at the front stage of any ADC, then you will get a thermal noise effect, and that also will add to SNDR or SNAD. So now suppose if you have, now we don't talk about like what are the different effects, we will reach to that, but suppose now you have an ADC and therefore you get some SNR after measurement at the output of ADC. Therefore, effectively, you expect that SNDR or SNAD to be less than that ideal SNR that you had for even full-scale signal. Therefore, now the number of bits effectively you can get from this ADC won't be the same number of bits that you expected here. So because here it says that if you have some SNR, if you have a number of bits n, you will get this maximum ideal SNR. Of course, this SNR increases if you increase input signal amplitude. This is for full scale. If signal is not full scale, you will have less SNR and it increases with the signal amplitude. Therefore, ideally, you will get maximum SNR, but signal amplitude is maximum. Now, if your SNR reduces why? Because now instead of SNR, you will have SNDR. So it means that your signal power to the noise and distortion ratio is less than what you expected, even for full scale input. Therefore, this means that you don't expect to be able to get same resolution that you had before. Therefore, that's why we define this effective number of bits. Means that really, if I have, it's same relation, only just you solve it versus n. Okay, n as a function of SNR now. If you just derive n as a function of SNR, it will be SNR minus 1.6 dB, SNR as a function, versus dB, of course, divided by 6.0 dB per bit, right? Unit of this 6.0 is dB per bit. So effectively, you will get less effective number of bits, because you have now less SNR. And then when you have less SNR means that you cannot have same resolution you could have had with an ideal ADC. So it is obvious. This ENOB, or effective number of bits, is a very common specification you will find in all data sheets for ADCs. So it talks about like what is really effective number of bits which can be achieved with this ADC, not ideally. So now just to give you one idea of nonlinearity in frequency domain, before going to this, tell you one thing. It will be good, all of you are familiar with MATLAB? Good. So therefore it is good to start just simulating a simple ADC, for example 3 bits or 4 bits ADC. You can use Simulink also, and then get these characteristics to get a feeling of how you can simulate at a system level, not at a circuit level. Do it just for practice. Then in the project we will have a part on MATLAB, but then at least now you can start just practicing and then learn how to get this FFT. Are you familiar with FFT? MATLAB does it for you, of course, but it is good to understand also the concept. Okay, so that's good. So one of the references, of course, here again for this portion, one of the references will be Ken Martin book, same as switch capacitor filters. And I had introduced one more reference also at the beginning. You can use it, but there are also some application notes. For example, this is from National and 2006. So Gray from National has a good application note on the characteristics of ADC. So I have just, he has done a very interesting experiment in MATLAB to see how FFT components change if you have a little nonlinearity. For example, here as you can see, first one is perfectly a linear characteristics. Okay. So therefore, when you apply a sine wave with a the frequency he has chosen is 45.0195 megahertz. I don't know why this particular frequency, but anyway. So you have this particular sine wave, and then you have a sampling frequency of 200 megasample per second. Now you take a 50. Therefore, you will get a peak here, and then this shows your noise floor. So one interesting experiment you do in MATLAB is, if you have an ideal ADC, okay, so therefore means that ideal ADC effectively won't have any nonlinearity. So if you have an ideal ADC, so when you simulate a perfectly ideal ADC in MATLAB with some number of bits, check whether this relation is valid or not. Okay, so if you simulate with MATLAB, you won't get this. So there is a reason behind that, but so for example, you can use a sine wave with any amplitude or full scale peak to peak, and then see whether this relation is valid or not. So the SNR you get, in fact the noise floor you get at the output, and then you calculate SNR based on that, will obey this relation or not. So before you check it, and then you will see this noise floor actually is not the same value you expect. So just to give you a hint is, when you do FFT, you know that what is FFT? FFT is essentially based on DFT, discrete Fourier transform. When you sample a signal, you will have n-point DFT, right? And then actually it will be converted into n-point FFT. So now, if you have n-point FFT, then means that suppose if you take a window in the time domain and then you sample a signal, okay? As you increase number of samples in this time interval, okay, don't change your window width, just increase number of samples. What do you expect to see with respect to quality of the sampling? Quality increases, quality improves, exactly. Because now you have more number of samples. This is exactly like that. you are increasing your oversampling ratio, which is helpful. Okay. So FFT proves, so I don't enter into the details. FFT concept proves if you increase number of samples in a given interval, not only your resolution in time domain improves, but also in frequency domain improves. And that is what is called frequency bin. So you may have, in fact, wherever you hear about FFT, you hear about frequency bin. This is a very well-known concept in DSP. So what does it mean? It means that you know that FFT components are 2 pi upon k, 2 pi k upon m, and m is number of FFT points in FFT, and k is an integer which will be less than m. So if you increase m, this means that resolution in frequency domain also increases. You have more samples at a particular at a given spectrum. You have more samples in that spectrum. So difference between two consecutive frequency in FFT, which is 2 pi by n, is called bin. 2 pi by m is called m point FFT. I don't say n because it will get confused with number of bits. M is m point FFT. So frequency bin also will be improved. So means that you will have better resolution in frequency domain. But that means that you need to increase number of samples for a given interval. This means that if you have a data acquisition card, you need to put a lot of memory on the card so that you will be able to collect a lot of samples, many samples. But the whole point is that what is done in MATLAB is that when you, because it shows you FFT components, and eventually the bin depends on the sampling frequency and number of samples you collect. So what it does is that whatever signal power you have, it will divide that signal power over frequency bins. Means that it will show you the density of power for every frequency bin, because it's like power spectral density. This is your power axis and this is your frequency axis. Therefore, it's like a power density. So, and because it is power density, therefore the effective power has been divided by this number of frequency bins. So that is the reason you will get less SNR. And in fact, that will be exactly 20 log 1 upon m. M upon 2, of course, because FFT also takes half of the number of points. So exactly 20 log 1 upon m by 2 will be the drift, or in fact shift in the level of signal power that you will see here. So you just check it and confirm how much the difference you will get. That depends on the number of samples. Suppose if you choose, suppose here, I don't know how many he has chosen, but suppose I think it is around 8,000 point FFT. So 8,000 point FFT divided by 2 will be around 4,000 point FFT. Therefore, now if you want to get your frequency bin, it will be actually 2 pi divided by this number, and therefore your power will be in fact divided by this number, because now you assign a particular power to every frequency bin. It's power spectral density. That's why it reduces. Anyway, so it was just a brief explanation why you may not get exactly same thing. But trend will be same, is that if you increase number of samples, you will get improvement in SNR linearly for an ideal ADC. Now what he has done is, he has just applied a little bit change. For example, here V out is equal to V in. Here V out is equal to V in to the power 1.05. Or for example, V out equal to V in to the power 0.95. Or for example, V out equal to V in to the power 1.02. So this means that adding a little bit nonlinearity and showing how these FFT components change. Now one interesting point is here. Suppose you have a sampling 200 megasample per second, just to get idea of the nonlinearity or harmonics in the sample signal. Suppose if you have 200 megasample per second sampling rate, you have right now single tone, okay, not two frequencies. Then right now we are not looking at intermodulation, but it's same thing, same nonlinearity. Suppose you have 45 megahertz, so you expect to have 2 F0, 3 F0, 4 F0. but practically you have sampling rate, right? And you know that eventually it is a repeated spectrum. So if you have 45, your second frequency of course will be around 90 megahertz, but third one will be 135, which is beyond fs by 2. So therefore, when you want to look at harmonics in a sample signal, because see, suppose if you have a signal and because of nonlinearities, you will get some harmonics, okay, analog signal. So what happens is that, means that your signal bandwidth is not limited anymore. Now, if you sample this signal, there will be aliasing, a little bit aliasing, because now you have harmonics, therefore your bandwidth is not. Because of this aliasing, effect of this higher harmonics will be folded, will come to the bandwidth. Because anyway your bandwidth is between minus fs by 2 and fs by 2. So it will get folded, will come, because tails of this will interfere with each other. Tails of this repeated spectrum, of course with attenuated amplitude, as you know, because of sync. So they will interfere with each other. So there will be aliasing, they will be folded into the spectrum. Therefore, when you want to calculate or find out what is the location of harmonics in a sample signal, don't go with just multiplying by N20, 2F0, 3F0 and so on. You see what will be the effective signal which will be in your bandwidth. So that's why I will give you an example, because these are some basic concepts which are important to understand. Okay, so for the same signal, see, ideally it's like that. So this is F, and this is, for example, your magnitude of signal X, F. So you have two main harmonics at F0, and then now you will have sampling frequency, and then ideally it will be repeated, of course, with a reduction in the amplitude. Now before sampling, okay, you have this signal. Now if you have nonlinearities, therefore you will have harmonics. So your signal is not limited in bandwidth. Now you will sample it. When you sample it, then means that in this, after sampling, then this is your effective bandwidth. So how you can get harmonics over here? Therefore notice, eventually suppose with this example, your sampling rate is 200 megasample per second. Your main frequency is 45, I give exactly same numbers that Gray has given, megahertz. Then it's showing some harmonics in some particular frequencies, and then you may have this question, how they have come up, where they have come from. So 2F0 of course will be 90.039 megahertz. That's fine. So this is in the band. Now look, so you have a signal which is distorted. Therefore, look, for example, your signal would be something like this after distortion. It will have some harmonics, F0, minus F0, then 2F0, minus 2F0, and so on. Okay. And eventually it may not, it may be, right now we just consider it as a single frequency, harmonics also will be single, so you will get this. So now, of course, afterwards, because it's not a perfect sampling, therefore your spectrum will get attenuated after fs by 2. So now see, if you have this signal, and then now you sample this signal, there will be aliasing. Therefore, now to see what components of nonlinearity come to your band, you consider those components which actually did after calculation, the effective frequency comes here. Because you have so many components, right? It will go from minus 2f0, minus 3f0, this side 2f0, 3f0 to infinity. So what you can do is that, for example, you consider this component. Suppose you have minus 3f0 component. Okay? Minus 3f0. If you add this by fs, because when you do sampling, so you will have main, then you will have shifted by fs, you will have shifted by minus fs, again shifted by 2fs, a spectrum shifted by. Now you look at the spectrum which is shifted by fs and the frequency component of minus 3f0. Therefore, you will have minus 3f0 plus fs. Now this will be in your band, right? So now if you calculate, it will be 64.9415 megahertz. So therefore, first harmonic, second harmonic, third harmonic is a folded version of third harmonic which has come by frequency shifting of fs. It is folded to the main band. And now continuing with that, for example, minus 4f0 plus fs, that will give you 19.922 megahertz. Then you can have from other side, for example, 5f0 minus fs. Now these are positive harmonics shifted to left. That tail also will come to your band. So therefore you will have 5f0 minus fs, which will be 25.0975 megahertz. All of them are less than, as eventually your fs by 2 here, 100 megahertz. All of them are less than 100 megahertz. And finally, even if you want to look at sixth harmonic, it will be, which is shifted to left, 7117 megahertz. So this is the way now to look at harmonics in a sample signal. And that is the way when you run FFT in MATLAB, it will show you harmonics at this frequency. Okay? So now coming back to the plot. So it will be actually good even if you repeat same experiment that Gray has done in MATLAB and compare your results with his results. Okay, that is a very interesting example. And of course, the software which is used, which has been used, there is a particular software they have had, because this is for ADC, particularly for ADC. But doesn't matter, you can just run FFT. For example, you can just run FFT and then your signal, instead of V in, you can use a sine wave, and then you will see the, and run FFT on a sine wave, say to the power 1.05. And then you will see similar results. Because after all, MATLAB also samples the signal and gives you the FFT components. And then eventually this level, like here is for ideal case, is minus 70 dB. This is called noise floor. So in any FFT spectrum, these are of course harmonics, as you can see, and these are exactly at those frequencies, example frequencies that are calculated now. You can cross check it. For example, this is 45, you can see. This will be that 64 something we had, 64.9. This should be that 90.039. And then eventually it shows that how these values change. So therefore, now noise floor still is around minus 70 dB, but harmonics now are higher. Okay, any question? Okay, so this was the first concept of nonlinearity. Another concept which is important in data converters is dynamic range. This has different, actually I tell you, some of these definitions are a little bit different in different textbooks and even data sheets. But overall they are conveying same message and they are explaining same characteristic. Only there might be a little change in the definition. So what is dynamic range? Dynamic range, even in a system, it may not be a data converter. It can be anything. Dynamic range of a system is the ratio of largest absolute value of the signal, which can exist in the system and then it's acceptable for the user, to the smallest absolute value of the signal, again, which can exist in the system and is acceptable by the user. Acceptable is that, tomorrow you may be okay with a SNR of 20 dB. Somebody else may like to have a SNR of 40 dB. Therefore, that defines your dynamic range. So, this is a general definition of dynamic range. Now, suppose you have an ideal ADC, okay, with n-bit resolution. Therefore, maximum signal you can have will be full scale. Minimum signal you can have will be LSB. Therefore, ratio of them will be 2 to the power n. So, therefore, in ideal ADC, dynamic range is 6n dB. So, because you don't deal with the signals which are of magnitude is below LSB size, right? Your resolution is limited to, you cannot detect signals which are less than 1 LSB within some range. At any center point, you have this resolution of 1 LSB. Therefore, the minimum signal actually you can detect, if you start from 0, your minimum signal will be just LSB itself, starting from first bit, LSB bit, okay. So, sometimes SNR itself is used as a definition of dynamic range. In some literature, you may find it. Therefore, know that this is same thing. There is one more thing which is spurious free dynamic range, SFDR. Here, this dynamic range doesn't consider the minimum signal which is possible. It actually considers what is the maximum harmonic you have, maximum amplitude harmonic you have. It considers that particular harmonic, and therefore ratio of your maximum signal amplitude to that harmonic amplitude, and therefore it is called spurious free dynamic range. So, eventually it is ratio of the input signal to the peak harmonic component, means that the maximum harmonic you have. Coming back here, for example, if you look at the second one, which is Vn to the power 1.05, you have a largest harmonic, at around 90 megahertz, above 90 megahertz. So, ratio of these two will give you SFDR. Ratio, of course, in dB, means that it will be 10 log. How importance of this? It is one measure of linearity. See, because when you look at THD, in THD you are calculating RMS value of entire nonlinearity, means that entire harmonic range. But usually what happens is that all harmonics, and definitely they don't have same amplitudes. And this is important to know that what is the contribution of the maximum THD, maximum harmonic with maximum amplitude. So, this is a more particular definition, because that gives you an idea really what is the difference between main harmonic and next harmonic, next strongest harmonic, and where it is located. Because some of these things may create some problems, like similar concepts exist in the mixers also. There you care a lot, because these harmonics which are generated may create intermodulation distortion. They create image frequencies. But here what is important is at what particular frequency you get this distortion. Suppose if it is very high, and then suppose your signal has some component in that particular frequency, and definitely then it will get distorted a lot. So it is important, suppose here it was a single tone, but suppose if it was a two-tone signal with a second tone at this particular frequency, then you would get a lot of distortion. So eventually this SFDR is an extended version of THD and SNR. It's trying to give you more information. In fact, there are so many specifications. If you want to get more precisely all the specifications of ADC, here I am giving you just more important one. So this is just an example again from Gray application note. So here I have a specified noise floor. So then you can check it with the simulation. So for example, this is a signal with 0 dB power, Next harmonic is located here, and therefore it is 65 dB below that. Therefore, your SFTR is 65 dB. And eventually it is called highest spore. So, it's not only amplitude, it's also sometimes important for us to see where this is, at what frequency it is located. Okay, now we come back to transfer characteristics. These were a few like SNR, dynamic range, SNDR, and SFDR. So these are some of the important specifications when we are looking at the nonlinearity and nonidealities of the data converter. So eventually even quantization is some sort of nonlinearity we are applying to the system, to the signal. Now in time domain or in DC case, which is a static case, what are the specifications? So coming back to the transfer characteristics, consider just the static characteristics. What eventually ADC does, it compares analog input with some reference values, right? And then if that reference value is below the signal, we will go to the next code. Next code will be generated and so on. So if you look, this comparison itself may have some error, right? When you compare two signals together, means that you want to see how x1, x2, okay, you are comparing x1 with x2. You want to see whether x1 is greater than x2 or not, but how much greater? Are you able to have resolution of close to 0 volt, for example, to say that, this signal is 1 femtovolt above another signal? It's very difficult. So therefore you have a limited accuracy. So that's why this comparison, inaccuracy is associated with the comparison. Inaccuracy associated with reference level. Here we write exact value of 1 upon 8. But it is not 1 upon 8, right? It is 1 upon 8 plus minus some delta. And that delta can be very small value. But definitely it is not femtovolt. It can be microvolt, it can be millivolt. So that leads to shifting these points, right, in real ADC. So this point will be shifted. Moreover, not only these points will be shifted, but also you may get, for example, some sort of bending, you may get some sort of increasing the slope of this line, any sort of deviation from ideal characteristics you will get according to what is the corresponding effect. So first effect, okay, first effect. Suppose you are using this comparators, and every comparator which is used, like here, every comparator, it can be one comparator and then you change its input. Can be 1 upon 8, 1.4, this center values. Your transition values actually will be half LSP below that, means that this is 1 upon 16, this is 1 upon 8 plus 1 upon 16, and this is 1 upon 4 minus 1 upon 16, or 1 upon 4 plus 1 upon 16, and so on. So suppose if you have a comparator which has some offset, okay, at the input. Therefore, if you apply a reference to one of the inputs, the other input is applied and it is your signal. So output of comparator will toggle only if your input is your reference value plus V offset plus some smaller value, which is resolution of the comparator. So therefore you expect trigger point to be exactly here, which is half LSP, but actually it will happen a little after that. So therefore here, in fact, it is just like you have shifted, suppose offset is constant and remains fixed, therefore it is just like you have shifted your plot or curve to the right, right? Because now effectively all your switching points have been shifted because of comparator offset to right. So this leads to some sort of offset error in the characteristics of ADC, and that is exactly the characteristic which is called offset error. What you observe is exactly like analog case. If you have an analog output versus some analog input, if there is an offset, you will get a shift to right or left, depending on the sign of offset. If it is positive, you will go to right. If it is negative, you will come to left. So therefore, here what happens is that everything remains same, only this line will be shifted to right. And exactly if you connect these center points together, suppose we have only offset, so the intercept of the line with x-axis will give you the offset. Means that how this point, which was actually 0, has been shifted to right or left. That will give you offset error. Fortunately, offset error can be compensated easily because you can compensate offset of comparator, for example. So therefore, it is possible to trim and adjust the offset and bring the characteristics back to the original case. So that is not a big issue eventually. Of course, if offset is not taken care properly, then what will happen is that you will face problem here. You may miss a code because it may happen that if it is more than 1 LSP, it will cross full scale. So that is important. So this is one effect. Another effect would be gain error. Gain error in the sense that if you look at this line, eventually if you consider it has a slope of 1, if you define 1 as, for example, 1 code per, look at this particular line from 0 to 1.8. So if we consider the slope of 1 code, okay, 1 code transition, 1 bit transition, divided by, and this is exactly LSP size. So 1 code transition per LSP is the slope of this line, or 1 bit transition. 1 bit transition per LSP is the slope of this line. But this is again an ideal case. It may not be same. The reason is because your reference values may not be exactly that reference value. So every reference value may have some small change. So you expect exactly your transition point to be here, but now your reference has shifted to left or right. Therefore, you will have some plus minus delta V shift of the center point everywhere. So this creates some sort of change in the location of these reference points. Now, if you connect them together, you will get actually some sort of nonlinear plot. But if you get the envelope of that, that will give you some change of slope. Because it depends how much error you have everywhere. If this error are not same, therefore you will get some change in the slope. Change in the slope eventually comes when these center points shift. For example, suppose you expect at this particular 1 upon 2 to be center point for this code 0, 1, 1. But what happens? It will be now center point for 1, 0, 0. Because now your reference values have shifted. And that is because your reference values may not be correct perfectly. And also there are other reasons also, like comparator resolution. So all come together and then will create this sort of gain error. What is called gain error is that still if you can approximate or plot the envelope here, I mean ideally it has been considered to be a line, but practically it won't be line. When you have a change in these values, this middle values, center point or these transition points, you won't get again perfectly a line. But if you get envelope of that line, then it may not have again same slope. Because simply, for example, you may miss a code here. Therefore, your slope definitely won't be 1 bit per 1 LSP, effective slope. Therefore, a slope will change. But still again here, gain also is possible. For gain also is possible to get adjusted, because again it is similar to offset. You can adjust values. So this is also a good news that is not also a big deal as such. And okay, so there, for example, here in this particular example, your slope is less than 1 transition per LSP. 1 transition per LSP, it is same thing, because if you shift this 2 to the power n to the denominator, you will get 1 upon full scale divided by 2 to the power n, which is 1 bit transition divided by 1 LSP. In time domain and still there is one more thing regarding static characteristics, which is nonlinearity, DNL and INL. So again, DNL and INL well defined in all literature. Here I have used a very old reference, but that is a good reference. That's why here they call it differential linearity, but actually it's differential nonlinearity now. Of course, in some textbooks still they call it differential linearity. Eventually, what does it mean? The same thing that we discussed now in a more precise way. Because when we talk about offset error and gain error, we are not looking at what will happen for a particular code, right? What at a particular 100 or 011 or something else. We are looking at the overall performance of ADC. But now when we are going with this DNL and DNL specifically, now we are looking at even INL, now we are looking at the code by code or bit by bit performance of ADC. Eventually it is same thing. Eventually it says that suppose if you have two transition points, so you expect difference between two consecutive transition points or two consecutive center point to be 1 LSB. But this won't be 1 LSB. So it may be less than 1 LSB, it might be more than 1 LSB because change in the reference values, non-uniform offset across comparators, offset drift with time, temperature as ADC is working. Therefore, you may get this sort of characteristics. So, for example, look at here. So, this is level corresponding exactly at this point. Code goes from all 0, 1 to all 0, 1, 0. Okay, so this is the transition point. At this point, okay, doesn't matter whether it is shifted or not, like you see, there is offset also. Now, next point, because in differential nonlinearity, we are not worried about what is the location of first point. What we are looking is, if you are here at this particular transition point, what is next transition point? And the next transition point, for example, is less than 1 LSB. Here is exactly half LSB. Therefore, you have a dynamic, differential nonlinearity error of minus 1 upon 2 LSB. Because you expect the next transition point to be 1 LSB plus this. But now it is 1 LSB, it is 1 upon 2 LSB plus this. So you have minus 1.2 LSB error. So this is called differential nonlinearity. Here it is the opposite situation. For example, here corresponding with all 0, 1, 1. This is the transition point. Okay, so you consider this point. Next bit, next code will be all 0, 1, 0. The transition point for that code has been shifted to some value which is 1.5 LSB above this. So therefore you have plus 1 upon 2 LSB DNL, differential nonlinearity. So means that now as you can see, your step sizes or segment sizes are not same anymore. And that leads actually to nonlinearity, because if you connect these middle points together, you will get now a curve. It's not a line anymore. Therefore, it's like that your characteristics now shows a distorted characteristic. It's not a perfect line. So that's why it is called differential. Differential in the sense that you are comparing difference between transition point of two consecutive threshold values. So sometimes in data sheets, if you notice, they may have given only maximum absolute value of DNL, because after all that gives you the worst case value. So similarly you can have for a DAC. Actually characteristic of DAC and ADC are very similar. Therefore I thought it is good also you look at and if you look at the definitions, usually DAC and ADC are together. Just you change the X and Y axis, right? Then you will get DAC characteristics. Your X-axis will be code and Y-axis will be values. But only point is that here you will have only points in DAC, because for every code you will get a single value. You will get just points, because in DAC, output of DAC is a discrete value. It's a quantized discrete value. So again, same thing for DAC. For DAC now, because it is analog at the output, therefore you look at deviation of this step size on Y-axis, not X-axis. Okay, so therefore I don't explain it again, it's same as ADC, but only just by changing the axis. So another point will be integrated nonlinearity. In integrated nonlinearity, we really look at the entire plot. As you can see, for example, for ADC, so you will have all points and then you will look at the change in all points. Okay. And then of course these are like it has shown, these are ideal transition points and these are actual transition points for every transition point, so that you will get differential nonlinearity. Now there are different definitions for integrated nonlinearity. Eventually, if you look at a particular point, okay, in DNL we are looking at two consecutive transition points and how these two transition points are different from each other. Okay, so this is a real transition point, this is a real transition point, how these two are different. In integrated nonlinearity, at a particular transition point, we look how much that particular transition point has been shifted. How much that particular transition point. For example, if I expect here to have 3 LSB as a transition point, but now instead of 3 LSB, I will get, I expect to be here 3 LSB plus 1/4 of LSB, but I will get minus 1 upon 2 LSB shift to left. So this is integral nonlinearity, means that I am looking at only a single transition point and how much it has shifted to left or right, how much error we have at a particular point. That is called integrated nonlinearity. Eventually that means that if you add DNL from first code, you reach to this particular code that you desire, say 0, 1, 1, you will get INL. INL is actually summation of these DNL values when you reach here. And INL always is measured after offset is corrected to 0. So means that first this plot, whatever it is, will be shifted to 0, offset will get compensated, and now INL will be measured. Because effect of offset should not come into the picture. Otherwise, whatever you measure and you think it is INL, it is actually INL plus offset. So first you compensate, and then now you see how much your transition point, which was suppose, for example, we ref by 4, right? So which is half of 1/4 of your full scale, now has been shifted by, say, 1 LSB, 2 LSB, whatever, depending on the performance you get from ADC. So it is just a definition. Okay, any question till this point? So these are definitions and these are static characteristics. So right now there is no time information here. We assume that ADC converts it properly, output settles, output bits are settled, and then we are measuring them correctly. So before going a few things about time characteristics, time domain characteristics, just validation, of course, it's very easy to derive it. I don't derive, but it's very easy to derive it. This SNDR or CNOT and THT is summation of all harmonics. I show them by AN. So it is not, difficult to prove it. So eventually, definition of SNDR. SNDR is signal and noise distortion ratio. Therefore, when you want to consider definition of SNDR, you have RMS value of signal divided by RMS value of quantization noise plus RMS value of harmonics. Now you proceed, then you will get this easily. And here, of course, this harmonics. If you are talking, I mean, this can be applied to anything, right? Can be a signal, but here, particularly in data converters, these harmonics, you be careful, like these are harmonics of a sample signal, the way we calculate. Okay, now going with time domain characteristics, some important time domain characteristics. So first of all, we assume always that, okay, so ADC is able to operate at any speed. What does it mean? Means that if you have a signal, therefore you have a sample and hold which is enough fast, it can sample, and then ADC also is enough fast to convert that to digital form, but it is not always correct. Therefore, there should be a very important measure or figure of merit which is conversion time. If you apply a signal, okay, suppose a sine wave, and you have one sample of this sine wave, and from the time this sample is stored, okay, already stored on sample and hold, from the time this sample is applied to ADC till you get the final code of corresponding to this sample at the output of ADC is the conversion time, right? So it is obvious, of course. Conversion time and sampling rate may not be same, right? Because sampling rate is something which is controlled by sample and hold circuit. Conversion time is the time which is controlled by the data converter. You may sample with a very high speed, but you may convert with a very low speed. It might be. It might be vice versa. Therefore, how these two work with each other, the point is that, okay, so therefore you can have several ADCs, right? You sample input signal very fast, but you pass sample alternately to this ADC so that they will get enough time to work. That is what is called time interleaving. You apply first sample to the first ADC, you apply second sample to the second ADC. Suppose you have 4 ADC. Third sample to the third ADC. So by the time you come back to the first ADC, actually you have passed 4 sampling cycles. So in fact, effectively each ADC will see 1/4 of the sampling frequency. So it will have more time to process. So therefore, conversion time and sampling time are not same. In fact, if you have a sampling rate, it may not be same rate that your ADC can work with. So that's why we kept them, it is kept separate. And one more thing which is very important is uncertainty in sampling time. Because sampling is done by the switch. And really, finally, what value is applied to the input of ADC is not perfectly known. At what particular instant. That is also something which is called in sampling systems as a aperture error. That is because of switch. There are other things also. Just give you an example. Suppose you have a sine wave, peak to peak full scale, okay, VREF or V full scale, if they are same. Okay, let's make it full scale. Everywhere we talk about full scale. With a frequency F0. Okay, you want to sample it. So, how fast this signal changes, therefore, maximum rate of change for this signal is when it is at the crossover points, which will be V full scale into pi F0, right? This is the maximum change in the signal. Now, if the sampling time has some uncertainty, the best thing is even one is switch effect, one is jitter effect in the sampling clock. So that gives you definitely uncertainty. You cannot say that this signal has been sampled at this particular time t0. Definitely there will be some uncertainty associated with this 0. Nobody can claim this system is able to sample at this particular time. So that is, we call that uncertainty delta t. Therefore, we would like to reduce it as much as possible, right? So there is an ambiguity window around t0 and your real sampling point can be any point in this interval, okay? How small this delta t can be? Of course, smaller better. So now what will happen? We have a maximum rate, for example, this for the input signal. This is just an example. Okay, and you have some uncertainty. We call it delta t for a given sample and hold and for a given data converter. Specifically sample and hold actually. So therefore now, during this delta t, how much your Vin may change, right? You may sample it here, you may sample it here. Therefore, this delta t is not known. So we calculate like in fact delta Vin. So this is max value. So will be V full scale Pf0 into delta t. Means that during this unknown interval, of course it is known, during this ambiguity interval, your Vin actually may change maximum by this amount, right? Therefore means that what is the effect? The impact is, if you have ambiguity or uncertainty in the sampling time, that will get translated to error. Because now it is like that your input voltage has been something and now it will be something else. It is supposed to be something when it is sampled. Now its value will change by the value of the. In fact, you have uncertainty in the voltage domain now. Because you can say that if I sample here or here, there will be this much error. And this error should not be more than half of LSB. Right? So therefore, otherwise you will lose codes. So therefore, this means that this delta Vin, this should be less than half LSB. Amount of error which is generated because of this delta t should be less than half LSB. This exactly put a constraint on this uncertainty. So your LSB size is determined by your number of bits. Eventually, if you will replace, it will be V full scale upon 2 to the power n, multiply by 2 will be 2 to the power n plus 1. Okay. So that means that if your signal has higher frequencies, is that if you increase signal frequency or if you increase number of bits, your delta t will reduce. You can just get an idea. For example, suppose if your V full scale is 1.2 volt and therefore your LSB size, this term actually will be 1 upon 2 to the power n. So we don't need even to calculate it. Anyway, suppose you have number of bits, suppose for example 10 bits resolution you want. And signal frequency, say video 20 megahertz. So your delta t eventually will be less than, I just replace, LSB will be V full scale upon 2 to the power n, therefore it will be 1 upon pi 2 to the power n plus 1 into f0. Can you just one of you calculate it? Just to get an idea. This should be in the range of picosecond. How much? 7.7 picos. Yeah, it should be. the range of, so this will be 7.7 picosecond. So this is the accuracy in the sampling of input. So means that your error should not go beyond this value. And of course, when you design, you want to make it much smaller than this, see, because there are accumulated effects. You have this uncertainty in the sampling. You have those DNL and INL effects, right? Therefore, you need always to make sure that accumulated effect of all these non-idealities will give you one LSB error, not more than that. So, inherently, ideal ADC has one LSB. So, you can add one more LSB, that is the best case. So, not beyond that. Okay. Okay, so therefore now these were actually most important characteristics, but there are more and more. So what we will do is that as we continue, we will now look at, because now it will be boring if I just explain the specifications. Now you have an idea of what are the non-idealities. Let's look at one architecture and then see now how non-idealities affect the characteristic of that architecture, how we can calculate exactly DNL and INL for a particular architecture. So that's why we start with flash ADC as a simple example and then see what is the effect of variation. As I said, architecture is nothing that I should teach you. It's very easy to learn, even you may know it before. What is important right from the beginning? If I have a resistive network which generates reference values, if I have a set of comparators which compare input signal with reference values, what will be effect of comparator offset? What will be effect of variation in this resistive network? Okay. Of course, flash ADC, if it is a large ADC, that itself has problem. But right now, we don't look at it. Problem in the sense that it is not cost effective. If you have 4-bit ADC, you need to do the power 4 comparators. It's not very at all cost effective. And then you are connecting all inputs together to the input side. Therefore, you will get a huge capacitance. So, therefore, it's not a cost-effective ADC for a very high resolution. Usually, flash ADCs are used only for medium resolution. Hardly 6 bits, not more than that. But 6 bits, it's okay. Can be taken care. But in general, because its architecture is very simple, it is good to start with that. When you see effect of non-idealities, then we can go with other architectures. Of course, there are different ways to generate reference values for a flash ADC. There are different ways for generating reference values. Now, I start from a simple case. Okay, so suppose you have a reference value. This reference is usually obtained from a band gap reference because that will give you the most accurate value. And that is the reason usually when I want to give you example, I specify VREF as 1.2. So that is the reason. So okay, so therefore suppose this is R by 2. All intermediate values are R and final is 3 by 2 R. And then you start getting reference values from these points. So first level V1 was Vref by 2 to the power n plus 1, right? Because it was half LSB. If you look at the ideal characteristic of ADC. So therefore we will get it 2 to the power n plus 1. Okay, and then we will continue. Therefore, in general, say for example, now V2. Now, how this is generated? Eventually, suppose for example, you have n number of bits. Therefore, what you need will be 2 to the power n comparators. Each one of these reference values goes to one comparator. Therefore, suppose 1, 2. Actually, this should not be 2, but it's okay. So as we start like 1, 2, 3, and how many reference values do we need? Because it is n bits. So eventually we need 2 to the power n reference values. So this will continue and then it will go to 2 to the power n. Actually, how many do we need? 2 to the power n or 2 to the power n minus 1? How many? We start from Vref and then finally, no, we don't reach to Vref itself. We will reach to 2 to the power n minus 1. For example, for 3 bits, it was starting from Vref by 16, reaching to 7 by 8 Vref. So therefore, it is 2 by n power n minus 1. Therefore, here, therefore, you need 2 to the power n resistors and 2 to the power n minus 1 comparators. So, V1, for example, this is R upon 2 and then summation of all these R values. So, we are adding just all of them. So, and all of them are equal except these 2. So, it will be like 3 by 2 plus R by 2, but still it will be like R. And you have how many? 2 to the power n into R, right? All are R. So, therefore, you will get same thing. Vref by 2 to the power n plus 1. It was just a, proof to show it will be same. And eventually V2 for example will be now R by 2 plus R, again R into 2 to the power n. Therefore, now you will add 1 LSB to this. Multiply by Vref. So, therefore, you will get Vref. This will be 3 by 2. So, this will be 3. To the power n plus 1. And so on. As you notice, difference between these two consecutive values is 1 LSB. This is second reference value, which is the transition point. Okay, so transition points and we had middle points. So these are transition points. So if you remember, we shifted everything by half of LSB. That's why you will see here it is half of LSB, then it is 1 LSB plus half of LSB and so on. Okay, so finally you will reach to the final value, which will be V. I call 2 to the power n m. Okay, it will be easy to V1 and Vm minus 1. We'll have all values. Eventually it will give you Vref into 2 to the power n minus 1 2 to the power n plus 1. Right? For example, for 3 bits, it should give you a 7 by 8 Just we can calculate, this is 7. Eventually it will be Vref. All these summations, it will be summation n from 1 to till this point. This is 2 to the power n plus n minus 1. In fact, this will be 2 because it will start from this r and then plus r upon 2 upon whole value, which will be r into 2 to the power. So this will be Vref r into 2 to the power n multiplied by, and this is 2 to the power n minus 1. So it will be r into 2 to the power n minus 1 plus r upon 2. Vref, this will be 2 to the power n minus 1 minus 1. So it will be 2 to the power n minus 2. So we factor 2, therefore it will be 2 to the power n minus 1 plus r upon 2 divided by 2 to the power, here we factor 2 n minus 1. This will be 1 upon 2. Okay, so therefore I correct this. This is 2 to the power n minus 1 plus 1 upon 2 divided by 2 to the power n minus 1. Which is eventually 2 to the power n minus 1 upon 2. Okay, anyway, so these are reference values. Now we apply to a set of comparators. So till now we consider all are same. Therefore, first point regarding non-idealities, very interesting point will be to, okay, I will stop it, just I tell you. Now what if every resistor changes by some particular value of L plus delta RT? Suppose simply you have a simple resistive divider. You want to look if there are mismatches between resistors, what will be the worst case? See, you never need to calculate all details. Always you just consider what is the worst case. And then just you calculate what is the worst case value you will get for this particular design. Therefore, we consider what is particular worst case mismatch, just delta R. And then for that particular mismatch, what will be amount of deviation in reference values? Accordingly, how much nonlinearity we will get at the output of ATC. So, I will stop it here. We will continue on Friday.